Hello everyone, welcome to a video for electrical engineering. This is for the West Electrical Engineering Club, and today we are going to look over our first project, which is RGB LED. So right here we have an RGB LED, and we will see how when you connect different parts of the circuit you get different colors. You have red, green, and you have blue. So, let's get into what electrical engineering actually is. So, this is our first project, and it's RGB LED Intro to EE. And so, it'll aim at introducing you to electrical engineering and its basic concepts. The first thing is, what is electrical engineering? Well, electrical engineering is what's called applied physics, and the idea is that we make physics and electricity do work for us. So this can be applied in many ways, but usually in electrical engineering, the way we apply it is by designing, by testing, by analyzing, and by fixing electrical systems. So electrical systems could mean anything. It could mean something as small as your phone, or something as large as the entire power grid of a nation. The first thing that we can learn about electrical engineering is the basics. And I separate this out into 3 main laws and 3 main concepts. So we'll start with the concepts first. The first concept is voltage. So voltage is a difference in potential. What that means is that, let's say we have a bucket of water here, it's higher up, so it has a higher potential than the bucket down here. That difference in potential and what we call pressure is the reason why the water travels from up here to down here. Alright, so the potential energy is getting converted into kinetic energy, which is the water moving through the pipes down to the second container. Right? So voltage is kind of the same. Voltage is a difference in charges. So in the charges themselves, since positive is attracted to negative, are a form of attraction, thus a form of potential energy. And so let's say this battery here is the same way as these two containers, where there's a high potential of positive voltage over here, and a low potential of negative or slash zero voltage here, right? And so in this way we understand that voltage is a difference and not a amount. It's not a quantifiable quantity of something. Like, let's say I have 5 milliliters of water. In this case, voltage is not like that, it's a difference. And so for the standard definition of voltage, it is said to be the amount of energy, aka joules, that it takes to push a coulomb. And a coulomb is basically like a bucket full of water. It is a certain amount of electrons. So in this case, 1 coulomb is equal to 6.25 times 10 to the 18th power. Really, you will never need to use that number. But basically, it's just to explain that coulomb is really just as simple as a certain amount of electrons. Right? And so voltage is really just the energy it takes to push that certain amount of electrons. So the second concept is called current. And so current is, the idea is that it's a coulomb per second. So going back to a coulomb, it's just a certain amount of electrons per second. So how many electrons are going through the wire per second? And as you can see here, let's say we imagine current as if a river, and the amount of water per second that is going through the river is equivalent to the amount of current going through a wire. Then we see here that bigger river with more water flowing through it is more current, while a smaller river is less current. Current is measured in amps, or it works with the metric system where it's kilo for 1,000 amps and then milli for 1,000th of an amp. Same here with voltage, so volts is the unit of voltage over here. And so then we go on to our last concept. Our last concept is resistance. Let me see if I can make things more legible for you guys. So resistance is basically the force that goes against voltage, and it limits how much current can go through. So if we think about resistance as two pipes, and one pipe is clear, another one is cloggy, the cloggy pipe, the stuff that's clogging the pipe, is the resistance. Because here, without it, the full amount of water is going through, there's no limit, and all of it's going through at the same time. When there's a cloggy pipe, not only is the pressure lower at the end of the pipe, but also a small amount of water. And it's measured in ohms, with the omega Greek symbol. Now we go on to the laws. So the first law, and it's quite well known, is Ohm's law. I is the symbol for current. It's the variable that you use in equations. And A, for amps, is the unit. V is the variable for voltage, and R is the variable for resistance. So the easiest way I like thinking of it is that the current is equivalent to the voltage over resistance. And so basically what this says is that the higher the voltage, the more force is put on to the current, so there's more current going through. The higher the resistance, the less that current goes through, because there's more force opposing the voltage, there's more force limiting the amount of current that can go through. So you have this quite well known silly little picture here where the voltage is the red dude, he's trying to push the current through the wire or the pipe, and the resistance is like, no, I'm not going to let you do that, and he has a rope around it and yanks it to limit how much current can go. Second law is Kirchhoff's voltage law. And what it states is that when you have a circuit, all voltages add up to 0. So right here we have the key with all the symbols. So a diagram, a circuit diagram like this one, is basically a way of representing real-life circuits using easy to draw symbols. LED stands for light emitting diode, by the way. Okay, so go back to Kirchhoff's law. So the battery, what it does is it brings up the voltage to 9 volts. So it goes from 0 volts to 9 volts, right? And each and every component has this thing called a voltage drop. So that means that, let's say if we imagine this as a roller coaster, the battery is like the lift. It lifts the car upwards so that it can go down the roller coaster, and each component is like a part of the ride, like loop-de-loops or like the curves or whatever you want to have on your roller coaster. So battery's the lift, lifts it up to 9 volts potential, and then the resistor lowers it to 2 volts because it has 7 volts across it. So this point is 2 volts, this point is 9 volts, and this is why it's important to think of voltage as a difference, because the actual voltage across the resistor is 7 volts. It's the difference between this point and this point, right? And then this point, which is 2 volts, gets lowered by another 2 volts, which equals to 0. So basically, this lifts up the roller coaster, and then you always want to end back down at ground, because if you didn't, that means you have floating people on your attraction, and that's not good, right? So all voltages add up to 0. All voltages go back down to 0. Funnily enough, with this analogy, is that in electrical engineering, 0 volts is usually called ground. There's an interesting reason why. Again, we do not have time for that in this video. Next law is another one of Kirchhoff's. It's Kirchhoff's current law. And it's really simple too. Basically, what it says is what goes in must come out. And so its idea is that if you have a circuit with only one path, the current across on any part of this path will be the same. So basically what that means is, if we go back to this pipe analogy, is that you have a certain amount of water going through this point. The amount of water coming in must be the same as the water coming out, because you can't just generate water, right? Same way, you can't just generate current halfway. So the current here has to be 7 milliamps, the current here has to be 7 milliamps, and so does this point too. Okay, so now that we've looked at all these laws and these 3 concepts, let's actually see if they work in real life. So what we have over here is series and parallel. What that means is that there's 2 types of circuits. one that has each component one after another, meaning that current only goes through one component at a time, and another that's in parallel, meaning that the current goes through multiple different paths at the same time. Now, parallel does not mean that the lines in the schematic are parallel, and so what do we need to observe in both of these circuits? Well, in this circuit, right, remember that every single component has a voltage drop and that all voltages must equal to 0? Well, that's what we're going to find today, right, with our circuit. And then, as you remember, the current stays the same because what comes in must come out, right? So we need to check that both of those are true in the series circuit. Right, so we're going to do just that right now. Let's build it. One of the good things about these videos, and the reason why I wanted to make them, is because I know that a lot of people have trouble building. So here I'll explain really quickly how the breadboard works and how to connect the components up if you're struggling. So the first thing is that you have two rails on both sides of the breadboard. They are not connected, and in this case they're not connected to each other on both sides. There's these holes over here where they're not connected. And basically the negative, or the blue rail, is ground or negative voltage or 0 volts, whatever. And then the positive is high potential or positive voltage, right? And you want to make a circuit which connects this one to this one, not directly but through components, right? And so the way you make connections is that you have these rows. So in this case you have these rows, so row 50, right? Anything connected to row 50 will connect it to row 50, right? So let's say in the beginning I take out this LED, and remember that the longer pin of the LED, if you can see, is the positive one. So there's a direction to the LEDs. You connect it to the positive and you connect it to whichever row. So in this case, row, 45. So you connect it to row 45. And then the next thing you want to do is you want to take a resistor, and these are all the same resistors. So that means each resistor has a certain value to it. This is 1K, meaning 1000 ohms. And so it will limit the current so that the diode doesn't blow out. That's why we use them. Right? So when you place it in, you want to make sure that one of the pins is connected to the same row as the LED, and then the other pin is connected to any row. Then what you want to do is you want to connect using a jumper wire. So this is a jumper wire. You want to connect one side to the same row as the resistor, rows being this way, not this way, right? So like that. And you want to connect it back down to ground. So this is a closed circuit. That means that current can flow through the components, right, diode and resistor, back down to ground. An open circuit is one where it can't. So if I disconnect the wire, there's no connection to ground. This is an open circuit. And a short circuit is where, let's say I take this wire, I connect one side to the ground, the other side to positive. That's when you have a direct connection between the two, and that's a short. That's not good. So let's connect our circuit. Right. So when we connect our circuit, our LED pops on, and that's good. That means our circuit works. So now what we're going to do is we're going to use the multimeter. So multimeter is this device here. Let me zoom out a little bit. So this device, basically what it does is it measures anything from voltage, current, resistance, and a whole bunch of other things that we're not going to cover today. So when I turn this on, right, basically what happens is you have these two probes. So these probes are connected, one to the positive side of the multimeter and the other to the negative. So right now we're measuring, I set it to voltage. So let me see if I can do something to help the visibility. Yep. So now you guys can see better. So how we measure voltage is that we put one end on one side of the component and another on the other side. And theoretically you should get the 1.9 volts, yeah, Let's see how Kirchhoff's voltage law applies to this. Let's see if it does. So right now we have around about 9 volts here. My connection is bad, so there's a whole bunch of reasons why the numbers will not absolutely line up, but they theoretically do, right? So number 2, we have 9 volts. So the batteries brought up the voltage to 9 volts. And now the LED, which is what I'm measuring across, brings the voltage down by around about 2, right? That's kind of what we saw with our previous numbers. And so now this point from ground, right, from the bottom is actually 7 volts. So 9 minus 2 leaves us with 7 volts over here compared to ground, right? When I say that a point has a certain amount of voltage, that's always the difference between that point and ground. Voltage is a difference, if you guys remember, right? And so the other component now drops the rest of the 7 volts, and if we can see on this point of the this side of the component that's connected to ground, 0 volts is left, right? So that basically means in a closed circuit, all voltages always add up to 0, because 7 volts, which we got across the resistor, plus 2 volts, which we got across the diode, is around about equal to our 9 volts. Okay. Kirchhoff's current voltage law seems to be holding up in our series circuit. Now let's test Kirchhoff's current law. So the way we measure current is that we disconnect the circuit, we make it an open circuit, right? So this is no longer connected, if you can see here really quickly. Yeah, no longer connected. And so what we do is that we set, and it depends on your multimeter how you're supposed to do this, but you set it to current mode, right? And then my multimeter seems to be acting up lately, but hopefully it works now. What you do is you make it part of the circuit. So what I'm going to do is I'm going to take this power cable or the wire that's connected to plus voltage, and I'm just directly going to make the multimeter part of the circuit through it. So that's 0.007 amps. That's the 7 milliamps, right? Which we saw in our theoretical diagram, right? So 7 milliamps going in. Now let's see what comes out of the circuit. And if you remember, what comes in must come out. So it should be the same. Oh, I have to connect the LED to power first. Right. Okay. Now we're closing the circuit through the multimeter, and it's around about our 7 milliamps. Isn't that cool? So, now that we see that Kirchhoff's current law works in a series circuit and Kirchhoff's voltage law works in a series circuit, let's test out our parallel circuit. Okay, so now it's time for us to build our RGB LED circuit, which is going to be our parallel circuit. So, the diagram for this circuit will be like this. So the idea behind it is that you have an RGB LED with 3 different diodes, and each one is a different pathway where the current can go through. For now, we're just going to assume that the resistor and diode are part like a one component thing. And in theory, what we should see, if Kirchhoff's voltage law applies, is that the voltage through each and every branch should be the same. Why? Because each branch is connected together. That means that so the voltage here and here must be the same because they're literally connected together, right? And so voltage remains the same in a parallel circuit, but the current should be different now. So before the current was the same, the voltage differed after every component. Now the current should split off, right? But what we should still see is that the current that should be coming out should equal to the total current coming in, right? And so let's test that by making it. Right? We have this RGB LED, and the idea behind the RGB LED is that it's just multiple of these, 3 of these smaller LEDs connected into one package, and it has 4 pins, and you might be like, why not 6 pins, right? 3 LEDs, 2 pins for each LED. Well, that's because it's a very smart design, and it basically has all of the positive sides of the LED connected to the same pin. So that means that you can still control each LED individually by determining how much resistance it has to ground, right? So what I'm going to do is that I'm going to remember where I placed my longest pin. So I'm going to say that it's row 40. So if you guys can see here, row 40. So row 40 is right here. And so longest pin goes in row 40. And I think that's the easiest way of memorizing where it is. Then I'm going to take a jumper wire and I'm going to directly connect its longest pin to power. Okay? So now it's connected to positive voltage. To finish the circuit, what we need to do is take a resistor and bring it back down to ground, right? Positive to negative, and that's how it completes the circuit. So you take the resistor back down to ground, it completes the circuit. And I'm just going to do it for each one through a wire so that I can disconnect it easily. Right? Because these are kind of finicky. Once you get them in, you can't really get them out. So what I'm going to do is I'm going to connect each pin to a different resistor, but I will not connect the power pin that's on row 45 to the same to a resistor, because that would just be circumventing the RGB LED, right? Because you're basically just connecting power directly to the resistor, directly to ground. You're not making it go through the LED, right? You need to make it go to a different pin to do that. So then I take my last resistor, and if you're having troubles, ask for a component whenever we're doing a club meeting. Ask for a tool, and we will give you pliers, stuff like that, to kind of, you know, make the pins straight, because they can be quite a hassle to deal with. So I like using these wires, different colors, to symbolize the different colors that for each pin, but they are no different. There is no difference between either wire, because they're just wires. It's just color coding, right? So now we have all of our different wires here, and let's see what happens when we turn it on. Flashbang. So I'll put my finger over the RGB LED so that you guys can see a little bit better without getting blinded. So now I can remove these two. You see that only red appears, right? So there's red, there's green, there's blue, right? And when you combine them, it makes cyan, it can make purple, or yellow in this case, sorry, or purple with blue and red, right? So that's really cool. And the RGB LED is actually, the way that our screens work is that they have a bunch of these RGB LEDs, and mixing the colors in different quantities give us all of the rest of the colors. So what we're going to do now is we're going to see whether Kirchhoff's voltage law and Kirchhoff's current law apply. Right? So for Kirchhoff's current voltage law, which is probably the easier one to measure for me right now because my multimeter is acting up, for Kirchhoff's current law, we will voltage law, sorry, we will just measure the voltage across each and every component. So we'll ignore what I said about each branch being its own thing, and for now, right, since we're doing voltage laws. So first thing we'll note is from power, right? So I'm currently hitting the okay, so it's 1.9, around about 2 if you caught it there. Right. So the next thing is the other LED, other colors. Alright, so this is blue, it's 2.5, or sorry, green 2.5, and then blue is 2.6. Okay, and then let's see, for the first one was 2 volts around about. This resistor should be around about 7 volts across it. For this one was 2.5, so this one should have around about 6.5. This one's 2.6, so it should have 2.4 or less. Or 6.3 or 4, yeah. So that's what we're seeing. And remember, the total voltage is 9 volts, so that means that for each path, Kirchhoff's voltage law is applied, right? So now, next thing we'll see is Kirchhoff's current law. So what we'll see first is the total current, or let's measure the current of each and every pathway. Right, so I'll disconnect the red, right, and I'll make it go through the multimeter. So I'll set it up here. I'll connect it to the right spot. Remember that when measuring current with a multimeter, voltage input is forbidden. It says it there too. And when you make it part of the circuit, it goes from blue light to white light, and you see around about 6.7 amps, like we did before. So notice how adding different branches won't change the current? That's because for each branch, the voltage is the same, and for the red LED specifically, nothing changed. The LED is still red, it still has the same 2 volts across it, and the resistor is still the same resistor. So that means that if you share current with multiple different branches, that won't take current away from a different branch if you have sufficient current to power the entire circuit. Right? So 7 milliamps here. Now let's disconnect the green one and make it part of the circuit. Make the multimeter part of the circuit through the green branch. Okay, white light. And we see that the current is lower. Huh, that's interesting. Well, the current, it's lower because green LED is a higher frequency, which takes more energy to produce than red. And so what we should see is that the blue takes most energy. So that means that the least amount of current will go through it. Right? So 5.66 around about, which is less. Right? Let's say it's 7 milliamps plus 6.5 or 6.4 milliamps and 6.0 milliamps. So that's around about 12.3 plus 7, which is equal to 19.3 milliamps, let's say. So in a parallel circuit, all currents should add up, right? What comes in must come out. And so when you have current coming out of a point. So let's see. Let's disconnect the red wire, and let's make the multimeter part of the circuit again. So I very carefully connect it here. You can see that it's around about 20 milliamps, which means that we've done our job, and Kirchhoff's current law seems to be applying so far. And well, to prove to you that the Kirchhoff's current law applies completely is I'll connect all the resistors to one point, right? That means that all the channels, all the branches are converging to one point. And then I'll connect the ground, right, through the multimeter. Okay, and it's the same. If you see a little bit of variation, that's again because me moving around and changing the contact will add different resistance to the probes, and that will change the current slightly. But as long as it's around about where it should be, that's exactly what we want, right? So Kirchhoff's current law seems to be applying to our parallel circuit. That's great. Now what we want to do is we're going to show Ohm's law again. And so how we're going to do that is we're going to add these things called potentiometers. So this is a potentiometer, and it's kind of hard to use, sadly. We need potentiometers for the club. If you have potentiometers at home, please supply them. But basically, when you turn this, it changes the resistance. So it's a resistor that changes resistance, right? And we're not going to plug in any numbers yet, but what we're going to do for certain is we're going to check to see if Ohm's laws apply, right? So this is an actual opened potentiometer, and what I like about it is it's very easy to tell what's going on. So the middle pin is connected to this little wiper that goes across this path of graphite on the outer edge. And so what happens is that the path of graphite is connected to these two outer pins. Actually, it looks like an ohm symbol too when you remove the wiper too, which is kind of funny. But basically, the more you move the wiper, which is right here, to one side, the less the path that the electrons need to take to get from here to the middle, and the less the resistance. But if I move it away, now the resistance between this point and this point is much higher, right? but the opposite for this side and this side, because now it's much closer to this pin. So that's the potentiometer. It's a variable resistor which we can control, and it has a lot of uses. So what we're going to do, and one way I suggest in organizing the circuit, is I like to use the jumper wires and then the resistors. So what I mean by that is that it's kind of hard to get the resistors to go from the RGB LED. Here, let me zoom in for you guys. It's kind of hard to get the resistor to go from the RGB LED to a specific point because you need to stretch them out and everything. So what I do is I put the potentiometer and then I connect the wire to either the middle or the outer point, because remember, the middle to the outer point is variable. The outer to the outer point, the left to the right point is always going to be the same total resistance. Then afterwards I take the resistor and I put it back down to ground. Right? And so you might be asking, why are we using a resistor if we already have this variable resistor? Well, the problem with the variable resistors is that if you turn it all the way to one side, you can create a short circuit, or you can directly put all the current through the LED, right? Because you're basically just putting zero resistance if you directly connect one pin to the other, or one side to the other. And so that's why you always put a resistor, no matter what. So I did the first one for you. So as you can see, you take the jumper wire, and this is obviously, you can do it any way you want, but you connect either the middle or the side pin to the jumper wire, right? And then you connect it back down to ground using a resistor. Now we have only the blue channel left for the blue LED. And so same thing applies here. One thing that you have to do is keep track of which side you connect, right? So in this case, right, if the resistor is on the left side, that means that turning it to the left will decrease. It will increase the brightness. Turning it the other way will decrease it. Okay, so now that we've built the RGB LED circuit with the potentiometers, meaning that we can control the light. So, for example, remove different colors, right? Let's say just red. You can make it dimmer or brighter, right? Okay, so I was always saying you can change the hue of it, you can make it darker purple, or you can make it magenta-ish, almost pinkish, right? So it depends on how you change the colors. And so, yeah, that's how our monitors work, right? They have 3 colors, RGB, and then depending on how they move and treat those colors. And so now what we're going to do is we're going to actually measure the current going through the channel, and we're going to see what happens to it as we change the resistance. So if we increase the resistance, what happens, and if we decrease it, so on and so forth. So we're just going to do this for the red channel. And again, we already know that the voltage across the channels will be the same because they're connected to the same places. And so if we disconnect the rest of these and we make it go through here without the potentiometer, we're basically going through the potentiometer because I'm directly connecting it to the resistor. We get, again, the same thing, 9.6, right? Okay, so right now it's at 5 milliamps, right? And what we can do is if we turn it all the way to one point, so if we turn it away, all the way away from the resistor, right, most paths, so this means that there's a huge path for the electrons to go through, there's a lot more resistance. What we can see is that it drops down to 3.5 amps. So, I guess that Ohm's law also works in our circuit. Great, we're not breaking physics. Which means that when we increase the resistance, the current goes down. When we decrease the resistance, the current goes up. Right? Makes sense. Yeah, so this was the RGB LED project. It is, hopefully, I hope you guys liked this project, and in watching this video will help you understand it better, because we usually never have enough time to, properly explain things without being in a rush and a hurry and everything like that. But this was the first video. Oh, you didn't see most of it. But yeah. Hopefully you guys liked it. If you have any comments or anything, please let me know. And one thing before you go is, remember when I said that voltage is equal to joules per coulomb and current is equal to coulomb per joule per second? Try figuring out what resistance is equal to. And if you figure it out, try understanding why it's that way, what those units mean, right? Because joules per coulomb, you understand, is the energy that it takes to move a coulomb. But what does the resistor mean? What do those units mean, right? So, and I hope to see you next time, where I'll be explaining the components project and explaining how the different components work. I'll always be referencing Ohm's laws, Kirchhoff's laws, so if you have any further questions, please let me know. Thank you so much for watching, and I hope you have a great day.